Okay. All right, can you people hear me? All right, okay, fantastic. Today I'm presenting everything around GSM. And I will start with explaining GSM a little bit. And then we start focusing on the security of GSM. And later on I'll introduce some device that you can use to receive GSM traffic. And ultimately I will tell you how you can crack GSM traffic, receive and crack, and hopefully listen to it. And then I'll try to get you excited joining our project. First of all, our project is public. Our project is public, and everyone is welcome to join. We have a wiki online where you can read what we are doing, and it's a whole group behind this. I'm just presenting it, okay? So everything was not engineered by myself. And ultimately, yeah, I would like to get you excited and get you to join us, our effort. Okay, let me start. First off, why are we doing this? We are doing this because no one else is doing this. This is always a good reason. If no one else is doing it, it's probably hard because no one else has done it. And we like doing hard things. We like doing things that no one else has done. We also do this because probably companies wouldn't like this. The mobile operator wouldn't like this if other people could intercept their traffic. And that's usually good motivation as well. If a big company doesn't like it, there's always something to get. And also I'm very happy to give this talk in Austria, because if you've heard, in Germany there's some new laws that makes this kind of talk and this kind of speech very dangerous to do and very, very problematic. Because in Germany they decided instead being able to look at the problem and talk about the problem, they decided you're no longer allowed to look at this problem, and the companies get away with having faulty security, and ultimately you suffer from this. So I'm very happy to be here and give this talk in Austria, which is always a nice thing. Okay, let's start. First slide. Well, we talked about this already. Let's talk a little bit about GSM. GSM is the largest mobile network. There are over 2 billion subscribers on GSM. This is 2 billion, okay? This is, I think that might be more subscribers on GSM than people have running water at home. So it's a lot of people on there. Let's talk about the GSM network. Very complicated map. It will get easier in a minute, but ultimately what you have on the left side is a mobile phone. Everyone has a mobile phone. The mobile phone talks to the base station. This is the air interface, and then it goes into the normal landlines to the central database. And you see a lot of interesting things here. You see AUC, which holds all your key information. You see routers and base station concentrators and all this. So what you have to realize is that your mobile phone is like a network plug. It's a network plug into the mobile operator's network. And with this network plug, you can do more things than just doing phone calls. You can query the database, you can retrieve location information, you can change location information, you can change location information of other people. You can do a lot of funny things, but we'll get to that more later. And because it's an air interface, it's more or less like the old times when you had hubs instead of switches. You hear everything. Whatever this person over there receives, you receive as well. It's a broadcast, okay? The radius of a GSM mobile phone is up to 30 kilometers. And this is 30 kilometers radius. So in both directions 30 kilometers. So if you have a good receiver, ideally you can receive from 30 meters this direction and 30 meters this direction. That's very, very long. I mean 30 kilometers, you're already in the next town from here, okay? It's very, very long. I'll talk later about why this is reduced and practically not possible. But this is receiving. This is when other mobile phones are transmitting. Obviously, you can transmit to the moon if you like. You only need an amplifier. You know, if you amplify a lot, you can transmit to the moon. You can tell a base station in Rome from here that you are now in Rome. Okay? I mean, it only depends how much power you put in. Okay. Ultimately, base stations are clustered into little cells, and they don't overlap these frequencies. But this is just to give you an idea. Each cell is maximum of 30 kilometers. In city centers, they are much more reduced. And you will see this in a minute why. This is a picture of a base station. You see them when you walk around. You see them on the rooftops. And usually they go into 3 directions. Each is a directional antenna of 120-degree angle. So they have 3 antennas per base station. And this picture taken in the UK, there's a base station in here as well. Okay, there's a base station in this tree. It's a 100% artificial tree. They are doing this in the UK because people start complaining about the massive amount of base station in their garden. So, well, I don't know. Okay, let me talk a little bit about phone. How does a phone work? And our first approaches. A phone these days consists of 2 processors. And a phone is an amazing device. It's a very fast processor. It's 200, sometimes 300 megahertz, 32-bit ARM architecture, okay? So you can do a lot of stuff with it. They do a lot of processing. And they come with 2 processors. They come with a baseband processor, which does all the GSM networking stack. And they come with the application processor. The application processor is usually what you see. You know, it's your calendar and your SMS and all the fancy stuff. And the baseband is just a pure stack. Okay, our first approach. We wanted to receive GSM signals. So we looked on the internet and see what's there. And what we found is that there's a Nokia phone, and this is a lot of phones from the Nokia DCT3 series. We choose the 3310, that was shipped for 2 years with debug symbols enabled. So Nokia shipped this phone with debug symbols in the phone between 2000 and 2003. So all these phones have debug symbols, and you can exploit these debug symbols. You can have fun with them. You can turn your mobile into a trace mobile. So connect it to a PC, you configure it in a special way, and all of a sudden you receive all traffic that is sent from the base station. All traffic. Okay, so you see, for example, traffic that is sent to your friend on the beacon channel, on the broadcast channel. And you can analyze this with the PC, and this helped us a lot. I bought my phone for €1 on eBay, and the shipping cost €12. So shipping was more than the phone itself. Then there are other ideas how we thought, okay, how can we intercept traffic? Texas Instruments, who's the world leader in these OMAP chips for receiving for processing GSM signals, they have target boards and development boards, which are rather expensive, $2,000, $3,000, and they are rather hard to get to. But you can program these boards, there's Linux running on there, and you can get access to the baseband chip, and you can access to the traffic that is coming to you, and you can also send your own traffic. Then there's a company called PicoChip. They are doing base stations for picocells, for little companies who want to put up their own base station in their own room, in their own office. And they are software-based, and they are having development boards as well, so you can use these as well. And then there's wireless 3G for free. And there's another company who has 100% software implementation of a base station running on real-time Red Hat. And yeah, you can modify it and start sending and receiving information. But we decided to use the USRP. The USRP is the Universal Software Radio Peripheral. It was developed by Matt Ettus, and he released, I think, 3 or 4 years ago. And it's a device that can receive any kind of traffic from 0 to 5 gigahertz. Any kind of frequency. And it's 100% software driven. You connect it with a USB cable to your computer, and you receive the signals. You define the frequency you want to tune in, you define the bandwidth, and all of a sudden you receive all the IQ signals, and you do all the demodulation on your computer. And there's a new project, a new radio project, who wrote a lot of tools and a lot of blogs to process this data. And we are using the same thing. Now, let's go into GSM signaling. GSM signaling works on different frequency bands and depends where you are, if you're in America or in Europe. But a famous one in Europe is the GSM 1800 megahertz band. And a GSM phone is either sending or receiving. It's never doing the same thing at the same time. Okay, this makes our design much simpler because we either have to concentrate on sending traffic or we can swap on transmitting traffic. We don't have to deal with both at the same time. And sending and receiving, it's also separated on a different band. They're 25 megahertz apart. So we can tune, when we're on one certain frequency, we know on this frequency there's only traffic from the base station, and when we're on a different frequency, we know from this frequency there's only traffic to a base station. Okay, the USRP costs $900, okay? It's not expensive. And considering the euro at the moment, it's really cheap. A limitation of GSM, and then I also explain why 30 kilometers is not really possible. Limitation of GSM is that at a maximum 1,000 people at the same time can do a phone call. If there are more 1,000 people, the frequency band can't handle it. Okay? So what they do, Obviously, there are more people at the same time now in Vienna doing phone calls. There are more than 1,000 people. So what they do, they make these cells smaller and smaller. They make them 2 kilometers small. They limit the transmitting rate. And then in a 2 kilometer cluster, 1,000 people can do a phone call. So if 1,000 people in a stadium, they all do at the same time a phone call, the network is jammed, and you get this famous network busy thing on your mobile phone. Maybe one of you had it already. That's a limitation. Okay. I talked about this already. It's either sending or receiving. The beacon channel. The beacon channel is a broadcast channel. The first thing your mobile phone does, it listens for all messages sent to everyone. It's like on a network sending to everyone. It's there as well. It's sent to everyone. Everyone analyzes it. And at some point, the base station says, I want to speak to this specific mobile phone. And then the mobile phone says, okay, this is me. What do you want? And the base station says, yeah, I would like to send you an SMS. Why don't you go on a different channel? And then all the communication happens on a different channel. But everything that is sent over the beacon channel, you receive as well with the Nokia phone, okay? So you receive, for example, information, this mobile subscriber just entered your cloud, you're receiving cloud. Or this mobile subscriber just left your cloud. This mobile subscriber just is at the train station or somewhere else. You see whenever someone initiates calls, whenever someone receives the calls, when someone sends a text, receives a text. You see the kind of encryption that they're using, and all this kind of meta information you get for free, unencrypted. Okay, some more facts. One burst lasts 156.25 bit. If you're a computer scientist, you start vomiting when you read a quarter bit. But when you're an RF engineer, you say, okay, it doesn't really matter. And really, it doesn't really matter. Okay, that's enough of the facts. This is an example output of the Nokia Trace Handy. So what we did, we connected the Nokia Trace Handy, and we sniffed or traced the traffic received by the mobile phone while receiving a text message. And this is a good example how you can see what's going on, what's happening on the beacon channel. What you see here is the base station asking for any kind of mobile phone with this specific temporary mobile subscription identification to respond if it's there. So, hello mobile phone, are you there? And then the mobile phone, and then the base station says, okay, I would like to do something with you, please go on a separate channel. And it assigns a separate channel. All this information is public. It assigns a separate channel. It tells the mobile station the channel hopping frequency and the channel hopping algorithm to use. And all this is all public, okay? The next message sends, okay, who are you anyway? And it says, yeah, my type of identity is IMSI. I would like to get your IMSI, your mobile subscription identification. And he says, okay, this is my IMSI. The mobile phone responds with the IMSI. And this is something fascinating, because if you read the GSM standards, it says the IMSI should never be transmitted over the network. Okay? So this was the first trace that we did. The first trace. And what we see is the IMSI being transmitted over the network. So this gave us hope. We just started with GSM. Okay? We started with GSM this year in 2007. This was the first program we ran. And what we see is already shit coming out of this. Okay? So, well, great. Let's continue. I told you the cipher to use. The base station says, okay, A5/2 is available, which is a weak encryption, and also A5/1 is available. The mobile phone should use a stronger one, okay? It might not always do so, but it should. The base station sends a random number to the mobile station, and the mobile station will encrypt this random number, generate an address, and then send this address back to the base station. The base station can then verify that this is really the authentic subscriber he wants to talk to. So address is sent back. All this is clear text, okay? And then the base station says, okay, let's start ciphering, but please also include your EMI. This is not just a subscription identification, this is now also your equipment identification. And obviously that's signed in clear text as well, including the software version. So everyone basically knows what kind of phone you're using. Also something that shouldn't be clear text on the network. Okay, let's see. GSM security. You know this picture? GSM network. Now, there are certain ways how you can attack a GSM network. how you can intercept traffic. Obviously, the most obvious way is you have the key already. Okay, easy to do. We don't talk about this. Another way is you just go to the base station. Only the interface is encrypted. As soon as it hits the base station, it's all clear text. It's sent over clear text, digital lines, throughout the network. So someone with access to the base station, and they are quite easy to access. If you look out of the window, some roofs go up, padlock, in, can read it. And there's an official interface, there's a monitor port, there's a switch where you take your laptop, plug in your laptop, use a certain kind of software, and you can intercept all traffic received from this base station in clear text, including voice, everything. Okay? So there's no end-to-end security on GSM. This is how far GSM security goes. Okay, this is the network, this is where it is secure. And, well, this was broken. This was broken in 98 already. Shamir and other researchers broke this in 98. But what they broke is a theoretical attack. They still required, I think the best attack right now requires 90 seconds of traffic. But that wasn't good enough for us. We wanted to crack anything. We wanted to crack any kind of SMS message that only lasts a couple of milliseconds. And in the end, I mean, most phone calls, over 90% of all phone calls are shorter than 90 seconds. So this attack was, okay, in theory GSM had broken, but practically no one can still break it. So we want to do the practical thing. Okay, about the standards. It all started with A5/1, the strong encryption algorithm. Now, when GSM started in the 80s, they were so excited about it that it had encryption, because the US, they didn't have any encryption, that they thought, oh, this is far too strong, and we can't give it to the Russians, and we can't give it to the Middle East, so we better invent A5/2, which we can crack, and then we can use it, and we can give it to them and sell it to them. And obviously A5/2 was cracked in a minute, and you can real-time just use a computer to intercept the traffic. For a long time in France, there was A5/2 was used so that the government can sniff on their own people. But that's not true anymore. That's still a myth that they're still using A5/2. We verified this with the trace mobile. They are using A5/1, which doesn't make a big difference because we're breaking it as well. Okay, another attack vector is be aware, your mobile operator knows your key. Okay, this is not your private key. There's no private public key authentication. This is a static shared secret generated by the mobile operator given to you on the SIM card. So somewhere the mobile operator has a database which contains all the keys of all subscribers. Anyone with access to this database can decrypt your traffic. Anyone with access to your SIM card can decrypt your traffic without having to retrieve the key from the SIM card. How it works, the SIM card has an interface where you can tell the SIM card, this is the random that you just received, and this is the GSM packet. Generate the key material, keep it secret, don't tell me what you generate, but just decrypt this packet. Okay? So with access to the SIM card, everyone can decrypt past conversation happened. So if today, for example, you do a conversation on a mobile phone, and you throw your mobile phone away and your SIM card away, and someone in 2 years takes your mobile phone out of the bin, he can decrypt all conversation you had in the past. Okay? Okay, let's see how A5/1 works. Let me check the time, how we're doing. Perfect. Okay. This is a shift register, A5/1. I'm not bothering with you explaining A5/2 because they are all coming from the same idea. It's a shift register of 64 bits. And what happens is you have your key, which is 64 bits. I'll come to that later. It's 64 bits. And it's fed into the shift registers, and they are clocked. You see 3 registers, R1, R2, R3. And you see these dark registers, these are tap registers. These are clocking registers. And yeah?
Hard to see a little your slide because of all the light here. Is it okay if we turn it off? Does it look?
Don't get scared. Okay.
I'm just not sure how to do this yet. We learn as we go. Where's the manual for the?
Okay, yeah.
If your laptop turns off now because you
Okay, so you have these clocking registers, and the clocking registers decide when to shift each register to the left or to the right. So let's assume all the registers are filled with some zeros and ones. And you want to clock it for one cycle to receive 1 bit of output. So the C1, C3, C2 determine which registers is shift, and this then depends which bits falls off at the end and is used for the output stream. Okay, so it's fairly simple, and it's fed back to the beginning again. There's no new input, just always fed back and comes in. And you see these different arrows here. This means that these bits are XORed as well and put back in at the beginning. So see these registers, the top register is 19-bit long, 22 bits and 23-bit, giving you a 64-bit key state. And well, one obvious attack is when you know the output stream, and you know the output stream because you're intercepting the traffic, and you set R1 and R2, you guess R1 and R2, you can calculate R3. Okay, this is an obvious attack. And the complexity roughly is 2 to the power of 42, which still means it requires you a couple of hours on an FPGA cluster. Not good enough for us. Not good enough. We want to be better than that. Okay, A5/1 encrypts per each frame. Each frame that is sent is encrypted under a different key state. And the algorithm generates 114 bit of cipher stream, which is then XORed with your plaintext, giving you the ciphertext. Okay, so the result is the ciphertext. And to understand, when you read the academic paper from Shami and other people, they say, yeah, you need 90 seconds, but you also need to know the plaintext. It's a plaintext attack, it's a known plaintext attack. You have to know the plaintext. And they say, yeah, you can guess the plaintext. You can maybe assume that each person in the beginning of a conversation says hello, or you can assume that only one of the person is speaking at the same time. So it gets really rather complicated. I mean, it's a theoretical attack, not a practical attack. But there's something much easier what they didn't know. We are coming from the GSM. We are not coming from the crypto community, we are coming from the GSM community. And we know that every GSM message is padded. It has to be 23 bytes long, 23 octets. So each message, if you can't fit enough data in there, is padded with the fixed byte, OX2B. Okay, so we have a lot of known plaintext. And in fact, the first message that sends is almost everything is padded except 3 octets. And also these 3 octets are always the same. So the first message, we have always known plaintext. And our attack only needs the first message, and we can crack. More to that later. Oh yeah, I said that already. Okay, our attack. We use a combination of rainbow table attack and others. So some of you might have heard of rainbow tables. If you come from the academic field, they're more known as CMTO, time memory trade-off attacks. And they were invented by Hellman in the 80s. And to give you a kind of understanding what they're doing is, let's go back to this one. You have a certain state, and this state generates 64-bit of output. Let's assume it only generates 64, not 114-bit. And what would happen if you take this output again, and use the output as a state and generate another 64-bit. And you take again the output as a state and generate another 64-bit. And you do it a couple of million of times until you hit a distinguished point. For example, until the first 20 bits output are 0. Okay? Then you have a start. You started with a fixed state. You go round, around until an endpoint. Now what happens when you sniff a cipher stream, you do the same with the cipher stream. You take the cipher stream, use it as an input again, and you do it as long until you have hit this distinguished point, until the first 20 bits are 0 of the output. And then you know, probably, hopefully, then when you start again with the original start point, and you do this again, you will hit exactly the state. You will hit the output. Okay, and this is called time memory trade-off attacks. And this is basically what we are doing. And we are modifying a little bit to work better on GSM. And A5 has a lot of collisions, so we had to get around this problem. Ultimately, last year, 6 months ago, we thought we can do it on 5 terabyte, and we would require 4 hours for one session. Now we have optimized this. We can do it on 2 terabyte, and we only need 1 hour for one session. And the complexity is 2 to the power of 30. So the first attack that I explained, the Rowan Anderson attack, where you guess one of the registers, was 2 to the power of 42, and we brought it down with the TMTO attack to 2 to the power of 30, which is good. Now, okay, let's go back to the TMTO attack. The simplest thing with the TMTO attack, or to attack this, is you would take a state, you would generate 64-bit of output, and you have the output. And you save these tuples. So you always save the start state and the output. Start state, output. So you would ultimately have to store 2 to the power of 64 tuples of each 128-bit long, which is quite a lot of data, and you can't really do it. And it's also quite a lot of processing power, because you have to do this 2 to the power of 64. Now, this is a stream cipher. And this helps us a lot, because, as I said earlier, you generate the output, and you check your cipher stream if you hit this output. But because you have 114 bits, you don't just do this from bit 0 to bit 63, you also do this from bit 1 to bit 64, and from bit 2 to bit 65. So you can do this 50 times. And because you have four GSM frames, you can do it 100 times. So this brings down our pre-computation time dramatically. We don't have to pre-compute 2 to the power of 64 records. We only have to pre-compute, well, far less, 2 to the power of 50 something, which is great, because then we can do it on an FPGA cluster in 60 days. And this is only the pre-computation. TMTO is always done in the pre-computation phase, where you generate these tables, and in the online phase. And the online phase is the actual attack, where you use the table to look up the values. And the online phase for the demo buster will take 1 hour in total. Now, we thought, okay, that's quite good, but we also have a commercial solution available. It's the A5 buster, and this will be available in 08. And we target to get this attack done under 30 seconds with a 95% probability, and it will be using 28 terabytes and a couple of FPGAs. And this will be the real-time online phase attack. The A5 demo attack we probably release around the same day. We will make these tables public on the internet. We are hosting it on the Internet Archive project. John Gilmer offered us this, and that's great because he said they have a couple of petabytes kicking around they're not using. So yeah, we do that with them. Okay. Let's think about the future. This is all nice and fine, we can crack GSM, but that's just a small thing. You can do more with GSM. You can do more when you have a USRP. You can start sending. You can pretend being a base station. You can have other people having logged into your computer, and you forward their calls, which is exciting. You can generate your own baby cell. Imagine you have a conference and you just serve your own mobile network. Everyone can do phone calls for free. You're in the city, you give the entire city free mobile phone calls. I don't know, it's not really legal, but you could do it. Well, obviously then the typical security assessment things, you can do man-in-the-middle attack, you can track people. Oh, tracking people is interesting. People always assume to track someone, you need 3 antennas and you do some kind of triangulation. That's not true. You can do it with 1 USRP. And that's great because the base station already gives you the information how far a mobile subscriber is, the distance from a mobile subscriber to a base station. So this is already known. Because you receive this information, you know where the base station is, you know the distance to your machine, you can triangulate them with just 1 receiver because you get a lot of information already. You get the phone numbers, you can get the phone numbers if you're interested in it. You can try to access the mobile operator database. Now, a typical, what can we do if we have access to the network? What's our next thing? What's the threat? What's the threat to the mobile operator? The threat to the mobile operator is that someone might take a look at the database. Someone might send packets that were not supposed to be sent. Buffer overflows come to mind, denial of services, who knows? I don't. Well, obviously free calls, we talked about that. And the next big thing is UMTS and 3G. Femtocells and picocells are already selling target boards, so you can experiment with that network as well. And yeah, ultimately, join us, join our effort. Feel free, everything is open. The last thing that we are currently using for sending and receiving traffic is the OpenTSM, which was a Spanish phone, which the source code is on the internet, and you compile the firmware on your own. You have access to the DSP, you have access to the baseband processor, and yeah, you can do a lot of things, and the things cost around 40 euro or so. And it's maybe a cheaper solution than the USRP. Ultimately, the USRP is more powerful because you can do more things with it. But for an entry-level GSM, interceptor, sending, pirate, whatever, OpenTSM is a good choice. And that's it. Thanks a lot. If there are any questions, please ask some questions. I'm sure there was something not so clear. Please.
I'm not sure if I missed it, but I think you didn't say anything about the security of SMS in this context.
Yes, okay. SMS, it's defined in the E2 documents as it's optional and left to the operator to encrypt it or not. So we thought, okay, usually when you leave something to the operator, you know, it's a disaster to happen. But actually we checked in the UK and France, and SMS are actually encrypted. So it's good news. Ooh. Well, it's bad news that A5 is broken, but it's good news that they thought about encrypting them. So SMS are encrypted in most countries.
Same encryption standard.
It's the same encryption standard as A5/1, exactly the same protocol handshake, the same security. Oh, I forgot to mention. I mentioned that the key state is seeded with 64-bit of keys. This is not true. The keys that are on your SIM cards are artificially weakened. The last 10-bit have been set to 0 to make it easier to intercept your traffic. Okay.
So SMS is sort of endangered in the same way as phone calls are.
Exactly. In the past attack, Shamir couldn't crack it because they said they need 90 seconds, but we only need the first frame, so we can get SMS as well, because obviously SMS are very short.
So does this open a window for sending out SMSs that pretend to be sent from another phone?
I don't know. At the moment, what we can do, we can receive the SMS and we can decrypt the SMS. It might be possible that you can also send. It's a field to research. Join us. Yes, please.
If I remember correctly, there are 3 linear feedback shift registers which are coupled in a non-linear way. But still, there should be some linear equivalent.
Yeah.
And do you know about the Massey-Berlekamp algorithm?
No, I don't.
Perhaps we should talk
You mean
a bit.
for...
It's going too technical, but it's a very efficient method to reconstruct linear and non-linear shift feedback registers.
Yes.
Perhaps easier than 2 terabytes.
Yeah, okay, let's talk about it. I know there's an attack where someone, I think it's called the Goliath attack, where the Goliath attack, or Golik attack, where he generated 64 polynomis. And if you solve all these polynomis, you can reverse the state. But the complexity is far higher than 2 to 30. But maybe if you have an idea, let's drink some beer and talk.
I'm not sure I understand everything. So if I have to buy this universal software right here and put it, link it to my notebook, I need 2 terabytes of symbol already stored on my notebook for decoding.
Okay, you buy this USRP from Matt Ettus, and you pay custom tax on it when it arrives, and you connect it to your PC. You need the GNU Radio software. You need our software on top of that, and then you can receive the encrypted data. Now, once you receive this encrypted data, you need 2 terabyte, which you can download from the internet in March 2008, and you need an FPGA card. You need an LX50 or Spartan 3 FPGA board, which costs, I don't know, $200 US, which does the online face cracking. And then you might be able to decrypt it. It's 95% probability.
No, but it's not possible to do it in real time.
Well, it takes, with the demo buster that we're releasing for free, it takes you 1 hour. With the commercial version, the A5 buster, it takes less than 30 seconds, which is as close as real time as you can get. I mean, you can always double your hard drive space and half the time. But 30 seconds should be good enough for me.
How much will it cost?
We don't know yet. We know the demo busters for free. We don't know how much the commercial version is. I mean, hardware costs will be around, I think, maybe 80,000, but we haven't decided yet.
Let's say you want to call somebody's phone call. Back in the day, on the Amsterdam network, Mark Lauder had some nice software that did this. You put in a phone number and watch it move from cell to cell, and you can dump it all to a WAV file or process it later. For this, you just pick a frequency and you see just who comes along, and you record it later on in the process? Or is there the public identifier of somebody's phone? You can just only record the encrypted traffic for, say, your target? and then post-process later.
Yeah.
I'm wondering if you can crack it, but how do you gather it in an efficient fashion?
Okay, first thing that happens is that every mobile operator has a beacon channel. So if there are 5 mobile operators, T-Mobile, E+, I don't know, each of them is in a different frequency. So when you turn in your mobile, it searches for its operator and logs in there and listens for all the traffic. Then the mobile operator, if you want to do a communication with the phone, says, okay, jump to this frequency and start exchanging data there. Now what you do with one USRP, we also jump on this frequency and we record the data. With one USRP at the moment, we can only follow one phone at the same time. You can find out, you saw earlier in the trace that you have this temporary MSI, and they were supposed to give you anonymity, but you've also seen that the EMI is anyway always transmitted, and the EMI SV is also, and everything is basically transmitted, so you can target a specific guy. You can even find out the phone number.
Right, until they change south, and you need another universal radio to listen to the other.
No, you only need a Yagi antenna or better receiver. I mean, your mobile phone might only transmit for 2 kilometers to be received from the base station, but with a good antenna, I don't know, you can do it from 8 kilometers or whatever, you know. It depends on the receiver.
So there's no real difference in that between the old analog days?
No, it's just not. It's just digital, so it's a bit easier to intercept.
Yes, you talked about the predictable padding. Could they easily change that, or would it break everything?
About what?
The padding, the predictable padding.
Oh, the padding. I don't know. They could possibly change it, but why bother? No one complains. I mean, did anyone of you complain that you're paying for the security and you never received it? People don't care, you know? That's the problem.
Should it also require updating firmware as well?
Say again?
Should it not require updating all the firmware on the mobile phone?
Yeah, possibly. You would need to upgrade all the firmware on all the mobile phones, yeah. That's true.
Mobile operators seem to use A53?
Apparently, some mobile operators are doing this already, but I wouldn't hope for that. I think the big move is to UMTS 3G. And when that will happen, obviously all mobile phones that come right now with 3G also can be downgraded. So you jam the other frequency band or 3G, and all of a sudden they all fall back to GSM, and then they're all insecure again. The FPGA code will be free available. It's Verilog code at the moment. And there's also a Unix C reference implementation, so if you want to port it to somewhere else, it should be fairly possible to do. Anyone else? Oh, yes, please.
So I'm here from Canada. I've got a SIM card with a password that's built into the SIM. I'm roaming over here on A1. How are the mobile operators sharing that information out of band?
How they are sharing this information?
The password on my SIM card.
The password on your SIM is a local SIM card. It protects your SIM card.
Period.
Purely. It doesn't. Yeah, it doesn't. I'm not aware that it goes over the network. So, from that, your 4-digit PIN is good enough for the SIM, maybe.
Sorry, one other bit of speculation. Why would they need to pad all the information, make it simple to crack it? All they can do is get it done encrypted back end. I mean, if you're law enforcement, you can get access to all this legitimately. Why bother downgrading any of it?
Because for the law enforcement, it's such a pain in the ass to get access to the BTS. I don't know why. But they artificially set all the things to 0. Maybe they bribed someone and the engineers of GSM and said, you know, you get 10,000, you set the last pin 10 bits to 0 and have a happy holiday, and he did it.
It just doesn't make sense that you got the skeleton key anyway.
That's right, and this is what we have to question, you know, why did they do this?
Yeah, that's true.
That's right. Oh, foreign agencies. Yeah, maybe. I don't know. Maybe. Anyone else? Oh, yes, please.
Yeah, there's one more question. What would prevent me from setting up fake base station here?
Yeah.
And by sending the strongest signal, getting all local phones to talk to me, and then providing nothing.
Nothing prevents you, and this is currently the most or the only exploited way for lawful interception who do not get permission to go to the base station. They set up a fake base station and they do a man-in-the-middle attack. So they say, I'm the strongest base station. I don't support any encryption, so everyone talks to me in clear text, and I just forward your calls, and you don't know about that. Because it's a one-way authentication. The mobile phone authenticates itself to the base station, but the base station does not authenticates yourself to the mobile phone. So you, as a mobile subscriber, you don't know if you're talking to a hostile base station or to the legitimate base station.
What you just said there is that the fake base station doesn't actuate encryption, but for the uplink to the real base station, I guess the real base station will require encryption.
No, it's not mandatory. So if the base station tells you, I support A5/1, and the mobile phone replies, oh, I don't support anything, and you're still allowed to communicate.
So if I would have a mobile phone which doesn't support encryption, I still can register to the GSM network.
That's right, yeah.
I guess that could be very easy. Are there phone calls which do not support encryption? Are there mobile phones which do not support encryption?
No, I don't know. The encryption algorithm is run on your SIM card, so it would depend on the SIM card. Maybe if you get a SIM card from some other country, you might find that they don't support encryption. There was actually a story in the newspaper a couple of months ago where they found out that if British people go to some countries that I don't want to name, their mobile phone are not encrypted to make it for their law enforcement easier to intercept. So they go to a country somewhere, and
if the base station found out, oh, that's
of course.
a user from the UK, I say I don't support authentication.
Encryption, yeah, of course. So the base station says, oh, there's a foreign guy in my country, probably my national security wants to sniff them, what they're up to. I just tell them, be clear text. And then the phone is happily clear text. Actually, in the first version of the phones that came out, you had a little symbol at the top, a little lock that told you when you have encryption or not. But it was demanded from the manufacturers to remove this lock so that it's not visible to the customer if he's encrypted or not.
That's not correct. It depends on the phone.
They exist again? Okay, that's great. For example, I see you have this Nokia phone, the 6630. You still see this lock when you do data calls, but you don't see it in voice calls. So when you connect your phone to a computer and you do AT, DT, whatever, then you will see this lock again, but not on voice calls. They removed it from the voice calls. Cool. Obviously, there's also software, the Nokia Field Monitor. You can verify if you have encryption or not. Anyone else? No questions? Well, thanks a lot. I hope you enjoyed it.